Hello, and welcome to Fall Asleep to Astronomy. I'm so glad our paths have crossed in this gentle corner of the night. Wherever you are, allow the edges of your day to soften and let the world outside become a distant hum. There is a deep, quiet comfort in the fact that we are all, at this moment, resting beneath the same immense, patient sky. Tonight, we'll turn our thoughts toward the great cosmic expanse, not to find answers that shock, but to explore an idea so curious and profound, it feels almost like a secret whispered by the oldest stars. It's about the very fabric of existence, and how something so grand, so infinite, might still hold a hidden, delicate vulnerability, a single point of failure that could reshape everything we see and know. We will wander through the latest scientific thoughts on the universe's structure and perhaps find ourselves wondering, what is the most fragile part of all this strength? We'll move slowly, following the distant light until the wonder settles softly in your mind. If this quiet exploration brings you a moment of peace, a soft like or a gentle subscribe helps others find this calming space, one sleepy soul at a time. The night is long, and we are unhurried. Let's begin. If the universe truly carries a deadly flaw inside it, a quiet crack in its foundations, why does it still allow us to be here, listening, wondering, existing at all? On the surface, the cosmos looks calm and eternal, like an old, patient sky that has always been and always will be. Stars drift across the darkness, galaxies swirl in slow spirals, and space itself seems steady enough to lean on. It is easy to believe that this stillness is permanent, that the universe is safe in the way a mountain feels safe beneath your feet. But deep beneath every atom, every star, every breath of light, there is something more delicate at work. Hidden under everything is a kind of floor, a field that saturates all of space. Physicists call it the Higgs field, though you can imagine it as an invisible ocean that everything is swimming in. Every particle you have ever heard of, every bit of matter your body is made from, is moving through this unseen sea. The way a boat feels resistance from water, particles feel the Higgs field, and from that resistance they gain mass. Without this field, there would be no atoms, no stars, no planets, no warm rooms, no you, and no me. In that sense, the Higgs field is like a silent sculptor of reality. It shapes what can exist and how. It quietly decides which particles can be heavy, which can be light, and how they can come together. Because of it, light can dance around matter instead of passing through without a trace. Because of it, time can pour itself through stable forms, rocks, oceans, hands, hearts. It is one of the reasons the universe can hold structures long enough for stories to arise. But what if that very foundation is not as steady as it looks? In the year 2012, when scientists at CERN's Large Hadron Collider announced that they had finally discovered the Higgs boson, the tiny ripple in the Higgs field they had been searching for, the world celebrated. Headlines called it the missing piece. Physicists spoke of the last stone in the grand arch of what they call the Standard Model, the framework that describes the known particles and forces of nature. It sounded like completion, like a full stop at the end of a long sentence. Yet for a few theorists in the crowd, the applause carried a thin, cold edge, because tucked quietly inside that discovery was a whisper, a mathematical hint that the Higgs field might not be resting in the safest possible way. Sidney Coleman, one of the quiet, sharp minds of quantum field theory, once warned, the vacuum we live in might not be the true vacuum. It sounds abstract, But what he meant is almost frighteningly simple. In physics, the word vacuum does not just mean empty space. It means the lowest energy state that space can settle into, the most relaxed position it can take. Coleman's suggestion was that our universe might only be pretending to be in that state. Imagine the Higgs field sitting in an energy landscape, like a ball resting in a bowl. If it were perfectly stable, the ball would be at the very bottom, with nowhere lower to roll. But Coleman and others began to wonder if our cosmic ball is not at the bottom at all. Maybe it is perched on a ledge, a false vacuum. It feels stable for now, but it is not truly safe. You can imagine it another way. Picture yourself standing on a frozen lake in winter. The ice looks smooth and solid. It holds your weight. The world is silent. But beneath the surface, cracks might be running invisibly through the ice, thin and waiting. As long as nothing disturbs it, you are fine. You can walk, you can breathe, you can look up at the stars. Yet, the possibility remains that one day, with just the right tremor, at just the wrong time, the ice could give way. The Higgs field could be like that. It behaves stable enough for galaxies to form and for life to grow, but deep down, it may be fragile. Quantum mechanics, the strange set of rules that governs the smallest scales, allows for something even more unsettling. Sudden, random changes called quantum fluctuations. One such fluctuation, perhaps born long ago in a distant corner of the universe, could, in principle, make the Higgs field tunnel into a lower energy state, a true vacuum. If that were to happen, every law of physics built upon the current state of the Higgs field would be rewritten in an instant. Physicist Joseph Liken at Fermilab once summarized this idea with chilling simplicity. The universe could spontaneously fall into a lower energy state, a true vacuum. That sounds like poetry, but it is a literal possibility in the equations, and if such a collapse occurred, it would not be a gentle shift. The change would sweep outward as an expanding bubble, a front of new physics pushing through the old, racing at the speed of light. Inside the bubble, the rules of nature would be different. Outside the bubble, everything would still be as it is until the bubble arrived. There would be no warning, because nothing can outrun light to tell us it is coming. There would be no pain, because the very structures that carry pain would be undone. There would be no survivors, because the universe we know would no longer exist in the form we recognize. It is called a cosmic catastrophe, and for once, that is not a metaphor. And yet, here we are. Around 13.8 billion years after the Big Bang, stars still burn, galaxies still drift, and the Higgs field still hums softly beneath every quark and every lepton, giving them mass and meaning. The most haunting part of this story is not that the universe might someday collapse into a true vacuum. It is that, by some delicate grace, it has not done so already. Why? One possible answer lies in the strange kindness of quantum mechanics. The same rules that allow impossible-seeming events to happen also allow highly unlikely situations to persist for a very long time. The mass of the Higgs boson, measured at around 125 giga-electron volts, places our universe in a special category physicists call metastable. Not fully stable, not destined to crumble immediately either, just balanced somewhere in between, like a door that is not quite latched but not yet swinging open. According to measurements from CERN and from Fermilab, it is the precise interplay between the Higgs boson and another particle, the top quark, the heaviest known fundamental particle, that sets this balance. If the Higgs boson were only a little heavier, Calculations suggest the universe would be firmly stable, the ball snug at the bottom of the bowl. If it were slightly lighter, the universe might already have decayed into a different state, long before stars, planets, or life had a chance to form. Instead, we find ourselves in an exquisite middle ground, the cosmic equivalent of a held breath. Cosmologists at NASA sometimes describe this as living on the edge of vacuum stability. Our universe appears to sit on that fragile ledge, not plunging, not entirely safe. In principle, the Higgs field could remain like this for trillions of years, longer than any human mind can truly imagine. Or, under the right kind of disturbance, some unimaginably high-energy event in deep space, perhaps the collapse of a massive star or a violent collision of exotic objects, it could suddenly shift into a lower state. This does not mean we are expected to fear every flicker in the sky. Instead, it serves as a quiet reminder. Even what seems eternal may be contingent. Stability on cosmic scales is not a guarantee. It is a circumstance, a phase, a gift with no promised duration. What makes this story so mesmerizing, though, is not the threat, it is the precision. Every equation written on chalkboards, every collision recorded deep under the ground, every whisper of the Higgs boson emerging from the data, all of it points to a universe tuned with astonishing care. Out of all the ways energy and fields could have arranged themselves, only a narrow band allows stars to ignite, atoms to bind, and consciousness to arise. And notice any of this. It is as if nature is balancing on a razor's edge, carefully poised between chaos and collapse. When the James Webb Space Telescope, often called JWST, peered back toward the earliest galaxies, those forming just a few 100 million years after the Big Bang, it saw stars already gathering themselves into patterns, already shining in coordinated clusters. That early, delicate order depends, in part, on the stability of the Higgs field. Change the Higgs field even by a fraction of a fraction, and the story could have gone very differently. The universe might have been dark, silent, and almost entirely empty. Physicist Richard Feynman once said that nature uses only the longest threads to weave her patterns, so that each small piece of the fabric reveals something about the whole tapestry. The Higgs field is one of those long threads unseen, but running through everything. To follow it with our minds is to peer into something like the nervous system of the cosmos, the underlying circuitry that lets reality feel solid and familiar. But even the strongest thread can fray. Coleman and others could not stop asking, what if the fraying has already begun, and we are simply too small in time to notice? Some theorists have suggested that cosmic inflation, the brief, wild period of rapid expansion right after the Big Bang, might have jostled the Higgs field into this metastable state. In that early chaos, space expanded faster than intuition can grasp, stretching quantum fields in strange ways. Others have proposed that dark energy, the mysterious pressure that is now speeding up the expansion of the universe, might be connected to the same underlying instability in the vacuum. Different ideas, different models, but they circle a shared theme. The universe's beauty and its fragility are not separate stories. They are two sides of the same equation. At CERN, researchers keep refining their measurements, nudging their instruments toward greater and greater sensitivity, trying to catch even the slightest hint that the Higgs field might drift over time. So far, all the readings point to an eerie balance, as if the universe were a violin string stretched with perfect tension, humming softly through space-time. Not slack, not snapping, just singing. Because of that, Every sunrise you have ever seen, every orbit of the moon around the Earth, every quiet moment you have spent under a night sky, all of it is possible only because the universe has not yet decided to let go of this state. The Higgs field still holds its shape. The illusion of permanence survives another day. We do not live in defiance of cosmic doom, but inside the grace of a temporary calm. The vacuum beneath us may be false in a technical sense, not the deepest possible reality, but it is ours. It is the stage on which every memory, every love, every question has unfolded. As long as it lasts, we can keep wondering, keep building telescopes, keep scribbling equations, keep looking up. Because maybe, in tracing what seems like the weakness of the universe, we are really touching the strength of its design, the way something so precarious can endure for so long and hold so much meaning. The night is long, and the equations that describe it grow deeper and more subtle. And somewhere between the quantum and the cosmic, another mystery begins to shimmer into view. What if the universe itself is not real at all, but only the vibration of invisible fields pretending to be matter? Is the universe truly real, or is everything you know just the shimmering of invisible quantum fields pretending to be solid? What if nothing you see, not the chair beneath you, not the floor under your feet, not the stars scattered overhead, exists in the way you have always imagined? Modern physics whispers a quiet, unsettling answer. The solid world you touch is not truly solid at all. The atoms that seem so firm in your mind's eye are mostly empty space, and even the tiny pieces inside them are not little marbles rolling around. At the deepest level we know, there are no tiny billiard balls spinning through a void. Instead, there are fields, quiet, invisible fields stretching across the entire cosmos, filling every corner of space, vibrating without rest. This picture is called quantum field theory, and it gently replaces our old idea of particles with something stranger and more fluid. In this view, what we call a particle, an electron, a photon, a proton, is simply a ripple, a small, localized wave in a vast ocean of energy. You do not really have an electron in your hand or in a wire. You have the electron field spread everywhere. When that field is disturbed in just the right way, it forms a tiny wave packet, a little knot of motion that behaves as if it were a discrete, single thing. That knot is what we name an electron. If the field stops vibrating in that particular way, the particle is gone, not moved somewhere else, not hiding, just absent, as if it had never existed at all. The ocean is still there, only the wave has passed. Astrophysicist Neil deGrasse Tyson once said that we are all connected to each other biologically, to the Earth chemically, and to the rest of the universe atomically. That is already a comforting thought. But quantum fields take it even deeper, because beneath atoms, beneath chemistry itself, those fields do not stop at your skin. They continue outward, through the air, beyond the clouds, past the planets, all the way into interstellar and intergalactic space. Every breath you take nudges them ever so slightly. Every thought that sparks in your brain rearranges tiny ripples in those fields. Every photon, every particle of light from a distant galaxy trembles through the same underlying medium that is humming inside your body right now. You are not just made of star stuff, you are made of field stuff. At CERN, in Switzerland, a ring of tunnels holds the Large Hadron Collider, often called LHC, one of the most powerful scientific instruments ever built. Its purpose is, in a sense, to grab the calm surface of the vacuum and give it a strong shake, just to see what ripples back inside it. Two protons are accelerated to nearly the speed of light and then steered into head-on collisions. In those moments, the energy is so intense that new particles briefly flicker into existence before decaying away. But if you look at it through the lens of quantum field theory, something more subtle is happening. The collisions do not create particles from nothing like magic tricks. They disturb the fields themselves. A wave moves through the ocean of reality, and for a fraction of a second, that wave becomes concentrated enough to look in a detector like a dot, a particle. Then the wave spreads, interferes, fades. In that sense, particles are like notes played on an instrument. The fields are the instrument itself, the wood and strings and air. Matter is the melody, energy, playing as it moves. Even the simplest experience, touch, is shaped by these invisible songs. When you place your hand on the surface of a table, your skin never truly meets the wood. The electrons in the atoms of your hand and the electrons in the atoms of the table never merge. Instead, they push against each other through the electromagnetic field, a kind of force-filled space that surrounds charged particles. What you feel as solidity is the pressure of two sets of vibrating fields refusing to occupy the same patterns. The sensation of touch is a kind of music too, the gentle resistance where waves overlap and push back. What feels like a solid barrier is really a chorus of quantum notes humming against each other. Scientists at NASA's Jet Propulsion Laboratory once described it in a way that feels almost like poetry. Everything in the universe is made of energy fields, interacting through invisible forces, and those interactions create what we perceive as matter. Even light, that most familiar traveler of the cosmos, is another of these field songs. Light is not a stream of tiny pellets racing through emptiness. It is the shimmering of a single, universal field called the electromagnetic field. Every beam of sunlight that has ever warmed your face, every flicker of a candle in a quiet room, every glint on the surface of the ocean is not a spray of separate pieces, but a pattern in that one field, vibrating across space. And yet, when we measure it, when our eyes, or a telescope, or a detector watches that ripple carefully, something curious happens. The extended wave shows up as a single photon, a point of light, arriving at a particular place and time. The wave-like spread of possibilities sharpens into one outcome. This is the heart of quantum mechanics. Reality behaves differently when it is being observed than when it is not. Not because consciousness is magic, but because measurement forces nature to choose among its many possible notes. Physicist Richard Feynman once called this the most beautiful and most confusing thing we know about nature. It is as though the universe carries an entire chord of possibilities and plays only one note when someone listens. If you could somehow shrink yourself down, not just smaller than atoms, not just smaller than the particles inside them, but all the way to the Planck scale, the tiniest realm we can meaningfully describe, around 10 to the power of minus 35 meters, that is, 10 to the minus 35 meters, you would see an even stranger world. At that scale, the fields are not calm at all. They fluctuate wildly. Even what we casually call empty space is not empty. It seethes with what physicists call quantum vacuum fluctuations, brief sparks of energy where pairs of particles and their antiparticles appear together, exist for an incredibly short time, and then annihilate, disappearing again. They are allowed to do this by the uncertainty woven into quantum mechanics. As long as they return their borrowed energy quickly enough, the vacuum is alive with this ghostly traffic. NASA's Chandra X-ray Observatory has helped us see large-scale clues that this restless vacuum is not just a theoretical curiosity. The mysterious dark energy that is driving the accelerated expansion of the universe may be tied to this underlying activity in the vacuum, the quiet, persistent hum of space-time itself, stretched across billions of light years. Astronomer Carl Sagan once said that we are a way for the cosmos to know itself. In the language of fields, that idea feels almost literal. The same fields that create the atoms of your body also ripple through the farthest galaxy the James Webb Space Telescope has ever seen. When Webb captured the faint, ancient light from a galaxy known as GNZ11, its glow traveling to us for about 13.4 billion light-years, it was recording vibrations in the same universal fields that vibrate inside you. Now, every particle, every photon, every atom in your body is just a wave in that endless sea, a coordinated dance of probabilities, described with exquisite precision by equations, but never truly solid in the way our senses suggest. The Planck mission, which mapped the cosmic microwave background, the faint afterglow of the Big Bang, revealed that the early universe was not smooth and quiet. It was a foamy, restless place where quantum fluctuations in these fields created tiny ripples in energy density. These ripples were smaller than atoms then, just little wrinkles in the cosmic fabric. Over billions of years, gravity stretched and amplified them. Those tiny irregularities became the seeds of galaxies. In that sense, the Milky Way itself, the galaxy that holds our sun and our night sky, was born from a wrinkle in a field. What we see as objects, stars, planets, cups, trees, hands, are only temporary concentrations of energy, standing waves in the cosmic ocean. A proton, sitting at the heart of a hydrogen atom, feels solid and eternal to us, yet even it is a storm of activity. Inside, quarks whirl around, and they are held together by another field, the strong nuclear field, mediated by particles we call gluons. Those gluons are themselves ripples in a field, binding quarks with a force so intense that it holds the core of every atom you have ever touched or known. From the nucleus of an atom to the filaments of galaxies stretched across intergalactic space, everything is vibrating. The very structure of space is a sea of motion, subtle, invisible, but always present. Because of this restless motion, physicists sometimes speak of quantum foam, a phrase for the fine-grained texture of reality at its smallest scales. It is not a flat, still fabric, but a constantly shifting weave of possibilities. The idea that you and I are made of waves in fields rather than solid pieces can sound unreal, like a metaphor gone too far. But the data keeps pointing to the same conclusion. Every collision recorded at CERN, every gamma-ray burst mapped by NASA's Fermi Gamma-Ray Space Telescope, every delicate pattern in the light captured by the James Webb Space Telescope confirms, again and again, that matter is not what it seems. It is more fluid, more musical, more ephemeral. So when you sit beneath the night sky, it helps to remember that you are not really under it at all. You are inside it, part of it, woven from the same invisible threads. The electromagnetic field that carries starlight to your eyes is the same field that carries the warmth from your heart and your skin into the cool air. The same quantum foam that whispers at the edges of galaxies hums quietly inside your atoms. The separation you feel between yourself and the cosmos, the sense that you are here and the universe is out there, is in many ways an illusion written by energy. And still, that illusion is beautiful. It allows you to say, I and sky, hand and star, even though they are different notes in one continuous song. From these waves, the universe builds structure. It shapes stars, planets, clouds, oceans, and living beings from nothing more than patterns in fields, mathematics, given a kind of gentle, persistent motion. NASA scientists have described it in simple, powerful words. From quantum fields to cosmic webs, reality is a continuum of patterns, energy folding itself into form. So when we ask, is the universe real? The softest, honest answer is both yes and no. It is real enough for you to see, to touch, to hurt, to heal, to love. It is real enough that gravity can hold your feet to the ground and the moon in its orbit. But beneath that everyday reality, it is a symphony of unseen forces, energy pretending to be matter. And if every field is connected, and every particle is just a ripple in that shared sea, then perhaps what we call gravity, that gentle pull holding everything together, is not a separate force at all, but the rhythm of the ocean itself. If every particle is just a wave in some invisible field, then where does gravity fit into that music? If everything else has been rewritten as vibrations and ripples, where is the wave that makes apples fall, oceans cling to earth, and galaxies swirl in patient spirals? Every known force in the universe has its messenger. Light carries the electromagnetic force through the photon, that tiny spark that lets atoms talk to each other and nerves send signals. The strong nuclear force, the one that locks the heart of the atom together so it does not fly apart, rides on the backs of particles called gluons. The weak nuclear force, the quiet hand behind radioactive decay and the processes that power the sun's heart, flows through the W and Z bosons. But there is one force, the oldest we have ever known, the gentlest and the grandest, the one that governs the motion of planets and the dance of galaxies, whose messenger has never been truly seen: gravity. The mystery is nearly poetic. We feel gravity in every heartbeat that tugs downward, in every step pressing against the floor, in the weight of blankets on a tired body at night. We see it in the curve of a thrown stone, in the tides pulled by the moon, in the patient orbit that keeps that moon circling the earth. It feels so familiar, so obvious, that it is hard to believe we do not fully understand it. And yet, when we zoom down to the quantum level, the realm where every other force is exchanged by tiny particles, gravity simply slips away. It does not fit neatly into the same boxes. Albert Einstein's general theory of relativity, published in the year 1915, is still the most beautiful picture we have of this invisible pull. In his view, gravity is not really a force in the old sense at all. Instead, space and time themselves, woven together into what we call space-time, can bend, twist, and curve. As Einstein put it, matter tells space how to curve, and space tells matter how to move. This simple-sounding idea reshaped everything. Planets no longer fall around the sun because some invisible hand tugs on them across empty space. They move along paths laid out by the curved geometry around the sun's mass, like marbles rolling along a warped rubber sheet. Gravity, in Einstein's universe, is geometry made real. Mass and energy reshape the stage, and objects simply follow the lines of that stage. But when scientists tried to bring that graceful, large-scale picture together with the world of quantum fields, the microscopic reality where particles flicker in and out of existence and forces are carried by quanta, the harmony faltered. The math that describes tiny particles and the math that describes smooth space-time refused to blend. Electromagnetism, the weak force, and the strong force all yielded to the quantum treatment. They could be described as fields with specific particles, bosons that carry their influence. Gravity resisted. If the universe is made of waves and vibrations, we are left with a gentle but insistent question. What carries the wave of gravity? What field ripples when a planet moves in its orbit? When a star collapses into a black hole? When two black holes spiral toward each other and merge in the dark? Physicists have given a name to the ghost particle that should, in principle, exist if gravity can be treated like the other forces, the graviton. In theory, it would be massless. It would travel at the speed of light, and it would have what physicists call spin 2, a mathematical fingerprint that matches the way gravity bends spacetime. If gravitons are real, then every falling leaf, every orbiting moon, every collapsing star, every step you take would be accompanied by a quiet rain of these particles, a chorus of gravitons whispering through the cosmos. But there is a problem. No one has ever detected one. The challenge borders on impossible. Gravitons, if they exist, would interact with matter so weakly that no detector we can realistically build would ever feel their touch. To catch a single graviton with any confidence, we would need an instrument larger than the planet Jupiter and more sensitive than anything humanity can currently imagine. Physicist Freeman Dyson once remarked that the probability of detecting a single graviton is essentially zero. It was his way of saying that, for all practical purposes, they may remain forever beyond our reach. And yet, even without catching gravitons, gravity reveals itself through ripples of another kind, waves not of particles, but of space-time itself. In the year 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, usually called LIGO, made history. They detected the faint tremor from two black holes colliding more than 1 billion light-years away. For less than a second, space-time passing through the Earth stretched and compressed by an amount smaller than the width of a single proton. The change was impossibly tiny, but the energy carried by that ripple was immense greater during that brief instant than the power shining from all the stars in the visible universe combined. Einstein had predicted these waves a century earlier, calling them ripples in the fabric of space-time. For decades, they existed only as lines in equations and quiet hope in the minds of physicists. Suddenly, we could hear them. It was as if the universe, after roughly 13.8 billion years, had finally sent us a clear sound from its deepest movements. Since that first detection, the LIGO detectors, together with their partners Virgo in Europe and Kagra in Japan, have recorded dozens of such events, mergers of black holes and neutron stars, sending gravitational waves ringing across space. Each event is another confirmation that gravity is not a static, silent pull. It is a living rhythm, a wave flowing through the geometry of reality itself. NASA and the European Space Agency are now preparing a mission called LISA, the Laser Interferometer Space Antenna, planned for the 2030s. Instead of using mirrors on Earth, LISA will place 3 spacecraft millions of miles apart in orbit, connected by beams of laser light, to listen for slower, deeper gravitational waves that ground-based instruments cannot detect. Scientists describe it as a kind of gravitational observatory that will be able to hear the deep bass notes of the universe, the long, low waves from supermassive black holes merging, perhaps from times when galaxies themselves were still young. All of this paints gravity as a wave, something that travels, carries energy, and can be recorded as it passes. And so the quantum question returns with a quiet insistence. If light waves are made of photons, And if electromagnetic waves can be counted in little packets, then gravitational waves, too, should have a particle description. At the tiniest scales, should they not be made of gravitons? Some researchers have begun to suspect that perhaps we do not need gravitons at all. Maybe gravity is fundamentally different from the other forces. Perhaps it is not a field in the usual sense, but something that emerges from the properties of space-time itself, a kind of collective behavior of many underlying degrees of freedom that we have not yet fully understood, like temperature emerging from the motion of countless molecules. Even though no single molecule has temperature on its own, others believe that at the Planck scale, distances around 10 to the power of minus 35 meters, unimaginably smaller than an atom, space-time itself stops being smooth. Instead, it might become grainy, like foam or a woven fabric seen up close. In that froth, at those scales, gravitons might finally make sense, emerging as natural excitations of whatever the true microscopic structure of space-time is. Observations of the cosmic microwave background, the faint glow left over from the early universe by satellites from NASA and the European Space Agency, carry hints of something subtle. If the infant universe experienced a burst of rapid expansion called inflation in its first tiny fractions of a second, that process would have created primordial gravitational waves, ancient ripples in space-time. Those ripples would leave behind a delicate fingerprint in the polarization of the cosmic microwave background light. In the year 2023, data from the BICEP array of telescopes and from the Planck satellite revealed tantalizing hints of such a pattern, suggestive but not yet definitive. If those signals are eventually confirmed, they would give us our first indirect glimpse of quantum gravity, a sign that gravitational waves, and perhaps gravitons, were already at work when the universe was barely born, whispering across time. For now, Einstein's relativity and quantum mechanics sit like two maps of the same territory, drawn in different languages. One describes a smooth, continuous world where space-time bends gracefully. The other describes a granular, uncertain world where fields fluctuate and probabilities rule. Bringing them into a single story has become one of the greatest unsolved problems in physics. String theory is one of the leading ideas that tries to build that bridge. In string theory, every particle, electrons, quarks, photons, and even the graviton is not a point at all, but a tiny loop or strand of string, vibrating in incredibly small, extra dimensions of space. Different vibrational patterns of the string show up to us as different particles. In this picture, gravity is simply one particular mode of vibration, often thought of as the lowest tone, the deep bass note of the universe's symphony. As theoretical physicist Brian Greene has written, in string theory, gravity is not something forced upon the equations from the outside. It emerges naturally from the allowed vibrations of the strings themselves. It is a hauntingly elegant idea, turning the universe into music made visible, or perhaps music made tangible. But string theory is not the only attempt. There are other approaches, like loop quantum gravity, that imagine space itself as woven from tiny loops, and more exotic frameworks that treat gravity as information or as an emergent statistical effect. None of them are proven. All of them are pieces of a puzzle we have not yet assembled. While the theories grow more subtle, our telescopes keep watching. The James Webb Space Telescope has already peered deeper into cosmic history than any instrument before it. It has seen galaxies forming earlier than our standard models expected, their stars clustering and their gravity sculpting structure faster than predicted. These surprises may one day whisper hints about how gravity behaved when the universe was very young. whether it followed the same rules then as it seems to follow now, or whether its quantum nature left an imprint in that early rush of formation. In every galaxy collision caught in Webb's deep images, in every swirling orbit traced by NASA's Hubble Space Telescope and by Webb together, gravity writes its invisible signature. It holds the fragile threads of the cosmic web together, guiding clouds of gas into stars, stars into galaxies, galaxies into clusters and filaments. And still, it eludes our attempt to trap it neatly inside the equations of quantum field theory. It is the thread we can feel but never see directly, the curve in space we can sense but cannot yet express in a single, unified language. Maybe that is part of what makes gravity feel so different. It does not just connect masses, it connects scales, from the quantum to the cosmic, from the smallest atom to the largest cluster of galaxies. It is the quiet rhythm that gives the universe its structure. The slow, steady beat beneath the quicker songs of particles and fields. And perhaps somewhere within that rhythm, the next great secret is waiting. Because if gravity cannot be found in the usual equations of particles, if it resists being quantized, then maybe it is gently telling us that our entire picture of the universe is incomplete. The quest for the graviton is not really just about one missing particle. It is about finding the final bridge between Einstein's smooth cosmos and the restless quantum sea beneath it. It is about the dream of a unified theory, a single language that can describe both the grand dance of galaxies and the delicate flicker of atoms, both the curve of space-time and the jitter of fields at the smallest scales. Until that dream is realized, gravity remains the most beautiful ghost in physics, the silent architect of everything we see, holding us gently to a planet that spins through space at about 67,000 miles per hour, while galaxies drift apart in slow, endless motion. And if every field hums its own song of creation, then gravity may be the heartbeat beneath them all. Yet one question still lingers in that rhythm, soft but insistent. If everything that has mass depends on this field called the Higgs, then how did the early universe first decide what mass even means? Why do particles have mass at all? If the universe's first impulse was for everything to be weightless, a moment ago we were asking how the early cosmos decided what mass even means. To trace that answer, we have to drift back to a time when the universe was young, hot, and almost perfectly symmetrical. In the very beginning, just after the Big Bang, the universe was a sea of pure energy. No place was heavier than any other. There was no real difference between what we would later call light and what we would later call matter. In that first tiny fraction of a second, according to the simplest versions of our equations, everything should have been massless. Every particle in the original, unbroken form of quantum field theory would have raced along at the speed of light, forever free. No resistance, no weight, no shapes that could hold together. But that is not the universe you and I inhabit. We live in a universe where some things move slowly, where planets cling to their paths, where your body presses gently into the ground when you stand. We live in a universe where energy can become form and stay that way for a while, where atoms can linger, bond, and build. The question sounds simple, almost childlike. Where does mass come from? But answering it changed physics forever. For much of the 20th century, many physicists believed that if you knew the fundamental particles, electrons, protons, neutrons, you could, in principle, describe everything. The world looked like a cosmic construction set made of tiny building blocks. Electrons orbited nuclei, protons and neutrons formed those nuclei, and that was that. Then the puzzle grew sharper. Light, carried by photons, has no mass. A photon can travel at the speed of light, by definition about 186,000 miles per second, tirelessly, never slowing down. But electrons, those tiny partners that live in the outskirts of atoms, do have mass. So do protons and neutrons. They cannot reach the speed of light. They lumber compared to photons. They feel resistance when pushed. They have inertia. Somewhere, somehow, that perfect symmetry of the early universe must have been broken. Something decided that some particles would glide weightless and others would feel heavy. In the 1960s, a small group of scientists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, began to suspect that two of nature's forces that seemed very different in our everyday world might actually be two faces of the same underlying interaction. One was electricity and magnetism, combined into electromagnetism. The other was the weak nuclear force, responsible for certain types of radioactive decay and for processes that power the sun's core. Their work became known as electroweak theory, and it suggested that, at high energies like those in the early universe, electromagnetism and the weak force merge into a single unified force. It was a unification so elegant that it would eventually earn them the Nobel Prize. But there was a problem, a crack running through the beauty of the equations. Those equations predicted that the particles carrying the weak force, the W and Z bosons, should be massless, just like photons. They should zip around at the speed of light. Yet, experiments showed the opposite. The W boson and the Z boson were heavy, with masses around 80 and 91 giga-electron volts, far heavier than a proton. Something was giving them mass, and the math, as originally written, did not say how. The missing piece was something that had not yet been seen, only imagined: the Higgs field. Peter Higgs, along with François Englert and other theorists, proposed that there exists a universal, invisible field spread throughout all of space. This field would fill the universe the way air fills a room or the way water fills an ocean, except it would be there, even in what we call vacuum. It would be impossible to step outside it. Certain particles would interact with this field as they moved. That interaction would slow them down, give them inertia, and in doing so, give them mass. As Higgs once described it, you can imagine particles trying to move through the universe as if they were moving through a room. If the room is empty, they can glide freely. But if the room is filled with a thick, sticky fluid like a sea of molasses, some particles will find it harder to move. They will feel drag, a kind of resistance. The Higgs field is like that cosmic molasses. Photons, the particles of light, are special. They glide through the Higgs field without feeling it at all. That is why light is massless and can move at the ultimate speed limit of the universe. But the W and Z bosons, electrons, and quarks interact strongly with the Higgs field. The more strongly they interact, the heavier they become. They gain inertia. They gain heft. They gain the property we call mass. For decades, the Higgs field and its associated quantum ripple, the Higgs boson, remained pure theory. The equations worked beautifully, but the key particle itself had not yet been observed. Then, in July of the year 2012, scientists at CERN's Large Hadron Collider finally announced that they had detected a new particle whose properties matched those expected of the Higgs boson. They were not just ticking a box on a list. They were confirming that reality itself has weight, that the vacuum of space, which looks so empty, is actually filled with something, a background field that gives form and substance to everything that moves through it. NASA once described it in simple, gentle terms. The Higgs field is like a cosmic glue. Without it, matter as we know it could not exist. It is astonishing to realize that every atom in your body, every molecule in the air you breathe, every planet tracing its orbit around a star, all owe their existence to this quiet field humming through the vacuum. Even the vast, almost airless emptiness between galaxies is thick with it in a way we cannot see. The Higgs field is everywhere, invisible but ever present. But the story of mass does not end with the Higgs field. In a way, that field provides only the opening note. While the Higgs field explains why fundamental particles like electrons, quarks, W and Z bosons have mass, it accounts for only a small fraction of the mass in the visible universe, roughly 1%. The rest, the weight of protons and neutrons, the heavy cores of atoms, comes from something deeper and wilder, the energy of the strong nuclear force that binds quarks together inside the atomic nucleus. In the theory known as quantum chromodynamics, often shortened to QCD, quarks are trapped inside protons and neutrons by gluons, the carriers of the strong force. Quarks themselves are surprisingly light, almost weightless compared to the proton as a whole, but they are held together in such an intense, restless dance by the gluon field that the energy of that confinement dominates. The constant exchange of virtual gluons, the ceaseless motion of quarks trying to pull apart and being yanked back in, creates most of the mass you feel when you lift your hand, when you stand on the earth, when you move through the world. Einstein's famous equation, E equals mc squared energy equals mass times the speed of light squared, is not just a nice idea on paper here. It is the fabric of your being. Your mass is, in a very real sense, the energy of tiny particles caught in loops of motion. At Brookhaven National Laboratory in the United States and at CERN in Europe, scientists use high-energy collisions to recreate conditions that echo the early universe. They smash protons together so violently that, for a fleeting instant, quarks and gluons are freed from their confinement, forming a kind of hot, dense soup, sometimes called a quark-gluon plasma. For trillionths of a second, detectors glimpse how pure energy congeals into matter, how motion becomes form. In those moments, we see one of nature's most delicate tricks laid bare. Matter as nothing more than energy folded in on itself, held in patterns. The James Webb Space Telescope also adds its quiet confirmations. By observing galaxies that formed only a few 100 million years after the Big Bang, Webb shows how the first simple atoms, mostly hydrogen and helium, began to gather into clouds, collapse under gravity, and ignite as stars. Inside those stars, nuclear fusion forged heavier elements: carbon, oxygen, iron, the ingredients of planets and of life. None of this would have been possible without mass. No mass, no stars. No stars, no fusion. No fusion, no carbon. No carbon, no life. But mass, for all its familiarity, is a fragile blessing. It depends entirely on the stability of the Higgs field. That silent ocean we swim in must keep its level just so. If that field were to shift even slightly from its current value, every atom in the universe would begin to change. The masses of particles would drift. If the change were large enough, atoms could no longer hold together. The structures of matter would unravel. In the most extreme scenarios, everything solid could dissolve into pure radiation, a universe of light and nothing else. This is not just idle speculation. Based on the measured mass of the Higgs boson, about 125 giga-electron volts, and the mass of the top quark, about 173 giga-electron volts, physicists calculate that our universe likely exists in what they call a metastable state. That means the Higgs field is not sitting at the lowest possible energy it could have. Instead, it is balanced precariously on a sort of plateau, not truly at rest, but not sliding either. Sidney Coleman called this condition a false vacuum, a state that behaves like the lowest energy state for an immensely long time, but is not absolutely final. In this picture, the universe is living inside a temporary calm that could, in principle, someday give way to a different, deeper configuration of the Higgs field. For now, though, the Higgs field holds. It hums quietly across spacetime like a cosmic heartbeat, maintaining the illusion of permanence. Through it, every particle finds its rhythm, its resistance, its weight, its reason to exist in a slow, tangible way instead of racing off at the speed of light. Carl Sagan once wrote that the beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. That structure, that pattern of form and function, is only possible because of mass. Without mass, the universe would be a lightless storm of energy, forever racing at the ultimate speed, never slowing down long enough to form stars, planets, or cells. The Higgs field is the quiet sculptor, turning motion into matter, potential into presence, energy into the shapes of stars and souls. Every particle's weight is a whisper of that invisible sea, a signature of its dance with the field that fills all of space. We are, quite literally, the ripples of that interaction made slow enough to touch, to hold, to feel. And yet, this calm sea has a history. The Higgs field, this soft ocean that gives form to everything, was not always as gentle and settled as it is now. Long ago, when the universe was still unimaginably hot, its perfect balance did not yet include mass in the way we know it. There came a time, as the cosmos expanded and cooled, when the temperature dropped just enough for that symmetry to shatter. The Higgs field chose a value, the old balance broke, and from that fracture, reality as we know it was born. When the universe cooled, something delicate and astonishing gave way. What shattered was not a piece of matter or a fragment of space, but a kind of perfection, a perfect mirror of symmetry. In the very first breath of time, there was no real difference between the forces of nature. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all of them were thought to be united, woven together as one. The early universe was so hot and so dense that every distinction we now know and name, mass, electric charge, even the familiar idea of separate forces, was blurred into a single, seamless field of pure symmetry. Physicists call this the grand unification epoch. It existed for less than about 10 to the power of minus 36 seconds after the Big Bang. That is, a decimal point followed by 35 zeros, and then a 1 in seconds, before atoms, before light as we know it, before time could settle into anything we might call a steady rhythm. At temperatures around 10 to the power of 27 Kelvin, roughly a 1, with 27 zeros after it, on the Kelvin scale, the universe was a blinding ocean of energy. In that furnace, everything raced at or near the speed of light. No particle could truly be called slow in that brief, almost unknowable age. The laws of nature were elegant and balanced. The equations that describe particles and forces would, in principle, have been mirror-perfect, so symmetrical that left and right, matter and antimatter, up and down, were indistinguishable patterns in the same glowing field. But like almost all perfect things, this state could not last. As the universe expanded, it began to cool, not out of intention, but as a simple consequence of growing larger. Stretching space thins energy, the way expanding steam cools off. And as the temperature fell, that perfect symmetry started to strain. The single, unified description of nature could no longer stay intact. One by one, the unified forces fractured. The strong nuclear force is believed to have broken away first, separating from the others, as the universe slipped below that extraordinary temperature of roughly 10 to the power of 27 Kelvin. With that separation, quarks, the tiny building blocks that would one day form protons and neutrons, gained the opportunity to begin binding together under their own special rule. A fraction of a second later, another fracture occurred. The electroweak force, once a single elegant entity, split into the two familiar forces we know today, electromagnetism and the weak nuclear force. And in that moment, something almost miraculous happened from our point of view. Mass appeared, not as a bolt from nowhere, but as a natural consequence of the symmetry breaking. This process is known as spontaneous symmetry breaking. The physicist Steven Weinberg described it with disarming simplicity. The universe did not really lose its symmetry. It chose one of its many possible faces. You can imagine a perfectly round ball balanced exactly on the very top of a smooth hill. While it is poised at the peak, the situation is perfectly symmetrical. The ball could roll in any direction: north, south, east, west, and the laws that describe that balance do not prefer one over the other. But the ball cannot stay at the peak forever. At the slightest nudge, it begins to roll, and it must choose a direction. Once it has fallen to one side, the symmetry is broken. Not because the hill changed shape, but because the system picked a path. In the early universe, the Higgs field was like that hill. At first, it sat in a high, perfectly symmetric state. As the cosmos cooled, the field rolled down into a lower energy configuration, choosing a particular value everywhere in space. The underlying laws remained symmetrical, but the universe, in effect, picked a side. That choice, that fall from perfection, is what gave us structure. When the Higgs field cooled into its lower energy state, it filled space with a kind of invisible resistance. Particles that interacted with it strongly gained mass, like swimmers pushing through thick water. Particles that barely noticed it remained effectively weightless. From that division, from that gentle imperfection, the universe we recognize began to emerge. NASA's Cosmic Origins program sometimes described this as the moment the universe acquired texture. Before, everything was too smooth, too symmetric for anything like solid matter to form. After, there was a pattern to the energy, a fabric with slight variations, dense and thin regions, slow and fast paths. That texture allowed matter to exist, to clump, to shine. Without that cooling, without that fracture of symmetry, there would be no atoms, no stars, no galaxies, no places for life to arise. But the price of that beauty was imbalance. In every broken symmetry, something is lost. A mirror is shattered, and one perfect reflection is never restored. In this case, the break seems to have produced a tiny but crucial difference between matter and antimatter. According to our best understanding, each should have been born in equal quantities. At the beginning, every particle of matter paired with a particle of antimatter, like twins facing each other in a mirror. But that is not what happened. For reasons still not fully understood, for every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny asymmetry, one part in a billion, decided everything. When matter and antimatter met, they annihilated. transforming into pure light, a flash of energy. But that little surplus of matter, that one extra particle per billion, did not vanish. It survived the mutual destruction. From those survivors came all the stars, all the planets, all the dust, clouds, oceans, and living beings we see today. As physicist Andrei Sakharov wrote, "The very existence of our universe as a place filled with matter is the direct consequence of a broken symmetry." The imbalance was not a flaw, it was a beginning. The European Space Agency's Planck satellite, which mapped the cosmic microwave background, the faint afterglow of the Big Bang, found subtle temperature variations spread across the sky. These tiny ripples, differences of only a few parts in 100,000, trace back to this era of broken symmetry. They are fingerprints of the early universe's unevenness, the seed patterns from which galaxies would later grow. Without those imperfections, the universe would be a nearly featureless fog. No clusters, no galaxies, no stars, just a smooth bath of light and nothing more. Even now, the James Webb Space Telescope is gazing back toward that epoch. It is seeing the first galaxies taking shape, massive luminous structures forming far earlier than theory once predicted. Their existence hints that the initial symmetry breaking may have been more dramatic or more intricate than we imagined. Perhaps multiple fields cooled and settled at nearly the same time, overlapping like waves on a freezing pond. As they solidified, their patterns may have imprinted subtle variations into the energy of space variations that later guided where matter would gather and where voids would remain empty. The universe might have layered its own complexity like strokes in an invisible painting. Symmetry breaking, then, is not just a tidy concept in an equation. It is a cosmic event that still echoes around us. At the smallest scales, within particle accelerators like CERN's Large Hadron Collider, we can briefly recreate hints of those ancient transitions. In collisions reaching trillions of degrees, space, for an instant, becomes fluid again. The familiar distinctions between particles and forces blur. Some particles momentarily lose their effective mass, as if the universe is remembering its earlier, more unified self. And then, just as quickly, the symmetry breaks again. The Higgs field reasserts its current value. Energy congeals back into particles with mass. Order returns. Each experiment is like opening a tiny window into the universe's memory, watching the first moments of time replayed at a scale we can measure. Yet one question still haunts scientists who stare at these patterns and numbers. Why did the symmetry break the way it did? Why this particular arrangement of laws, this exact balance of mass and energy, this specific universe? Mathematically, the Higgs mechanism could, in principle, have chosen countless possible outcomes, different values of the field, different strengths for the forces, different masses for the particles. Most of those choices would not have allowed stars to form, chemistry to unfold, or life to awaken. And yet, somehow, the universe settled into this one, a cosmos stable enough to endure, but fragile enough to evolve. Some physicists, like Frank Wilczek, describe this balance as the universe's hidden music. Every particle's mass, every force's strength, is a note in a grand symphony born from that broken mirror of symmetry. The European Space Agency once phrased it in a way that feels almost like a story. Symmetry breaking is the universe deciding how it wants to exist. In cooling, the universe chose complexity over perfection. It allowed small deviations, tiny imbalances, subtle textures. That choice is what made everything possible. Stars, planets, molecules, memories. Yet within that decision lies a quiet danger. Because if the universe could choose one stable configuration once, could it someday choose again? If the Higgs field were ever to shift, even slightly, if the underlying symmetry were to break once more in a different way, all masses, all forces, all forms of matter would change or vanish. At the deepest level, the rules that define atoms and light and time could be rewritten in an instant, with no warning and no way to resist. For now, the cosmic mirror remains fractured but steady. Its cracks are frozen in time. Its broken reflections build stars and galaxies instead of falling apart. Every particle carries, in its mass and its interactions, the memory of that first break, a trace of imperfection, encoded in its very existence. That memory whispers to physicists, to telescopes, to colliders. There was once a moment when everything changed, and in that whisper, another mystery begins to take shape, unsettling even the calmest minds in physics. Because what if the Higgs field, the same field that shattered symmetry and gave birth to mass, is not resting in its lowest possible energy at all? What if beneath its calm surface, it is only trapped, suspended above a deeper, darker reality, still waiting to awaken? What if the Higgs field is not calm at all, but simply stuck? From where we sit, the universe feels so still. Stars drift quietly through the dark, like slow lanterns on an endless sea. Galaxies spread across the void, like frost patterns on a window pane, delicate and sprawling. The laws of physics seem to hum along in perfect rhythm, constant and dependable, like a clock that has never once missed a beat. But what if that calm is only a surface story? What if the entire structure of reality is balanced, not on solid ground, but on a thin layer of unstable energy, a frozen lake that only looks safe, its cracks hidden just beneath the ice? Physicist Sidney Coleman was one of the first to ask this question in a serious, mathematical way. He turned his attention to the Higgs field, the invisible ocean that gives mass to all particles, and wondered whether it was really sitting in its true resting state. In a paper from the late 1970s, written with Frank DeLucia, he suggested something quietly terrifying, that the universe might be living not in a true vacuum, but in a false one. In quantum physics, a vacuum is not nothing. It is the lowest possible energy state that a field can settle into, the calmest configuration nature can choose. But there is a subtle twist. A field can get stuck in a state that feels like the lowest energy from the inside, while a deeper, more stable state actually exists beneath it. That kind of not quite final resting place is what physicists call a false vacuum. To picture this, it helps to imagine the Higgs field as a landscape of hills and valleys, stretching out in all directions. In the early universe, when temperatures were unimaginably high, the field fluctuated wildly over this terrain, jumping from ridge to ridge, never still. As the cosmos expanded and cooled, the Higgs field eventually settled into a valley that is the state we live in today. But according to Coleman's mathematics, the valley we occupy might not be the true bottom of the landscape. It could be just a shallow dip, a temporary basin surrounded by deeper wells of energy that we cannot yet reach or see. In his language, if our vacuum is metastable, it means we are living on borrowed time, poised in a state that is stable for a very long while, but not forever. This idea, simple in words, but devastating in implication, is known as vacuum metastability. It might sound like an idle speculation, but it is tied closely to measurements in real experiments. When physicists at CERN finally measured the mass of the Higgs boson in 2012, about 125.1 giga-electron volts, read as 125.1 billion electron volts, they discovered something peculiar. That particular value placed our universe right on the boundary between two possibilities. If the Higgs boson had been significantly lighter, the equations suggest that the Higgs field would already have decayed to a different vacuum long ago, erasing the structures we see. If it had been much heavier, the field would likely be perfectly stable, settled in a true vacuum that would last indefinitely. Instead, our measured Higgs mass sits in the in-between region, the metastable zone. NASA's Goddard Space Flight Center once described it in gentle, careful terms. The universe may be in a precarious state, balanced between two forms of vacuum. One supports the existence of matter as we know it. The other would erase it. If that balance were ever to shift, if the Higgs field were to tunnel through the barrier separating our false vacuum from a deeper, true vacuum, the result, according to our best calculations, would be instant and total transformation. You can imagine it as a bubble of lower energy vacuum appearing somewhere in space, perhaps in a distant, unnoticed corner of the cosmos. Inside that bubble, the Higgs field would take on a new value, a new equilibrium. The bubble would then expand at effectively the speed of light, sweeping outward and rewriting the laws of physics everywhere it passed. Atoms would lose their familiar structure. The strengths of forces would change. Even light itself might behave differently. There would be no warning, because nothing can outrun the bubble's edge to tell us it is coming. There would be no pain, because the very structures that carry sensation would be altered in an instant. Just a silent wave passing through the universe, erasing everything it touched and replacing it with something new and alien. Coleman once pointed out that you would not even know it had happened. The destruction would arrive at the speed of light. There would be no time for regret, no final moment to understand. It sounds like science fiction, like the plot of a cosmic thriller, but the underlying mechanism is grounded in the same quantum physics we rely on to describe atoms and radioactive decay. Quantum mechanics allows systems to tunnel through barriers they could never cross by simply rolling over them. Electrons do this inside atoms when they jump between energy levels. Particles do it when unstable nuclei decay, turning into other elements. If the Higgs field can tunnel too, then, at least in principle, it could one day transition to that deeper state. The equations do not forbid it, they quietly allow for it. There is something chilling in that, but also a strange elegance. Even the potential mechanism of cosmic destruction would follow the same rules that gave birth to stars, atoms, and galaxies in the first place. The Higgs field is not malicious. It does not want to destroy. It simply tends, like all physical systems, to evolve toward equilibrium, to slide down to the lowest energy it can find. The European Space Agency has modeled how such a vacuum bubble might propagate according to our current equations. If such a bubble were to form, say, in a distant galaxy halfway across the observable universe, we would never see it coming. It would race toward us faster than light could carry any warning. By the time its leading edge reached our region of space, our instruments and our eyes would still be calmly looking out at an untouched cosmos. Inside that new vacuum, the constants of nature, the speed of light, the strength of gravity, the mass of the electron would likely take on new values. Chemistry as we know it would fail. The building blocks of atoms might fall apart or rearrange into unfamiliar patterns. Matter in its current form could not survive. And yet, despite all of this, we are still here. The night sky is still there when you look up. Atoms are still holding together. Why? One answer lies in probability and timescales so large they are almost impossible to feel. even if the Higgs field is metastable. The calculated timescale for its decay could be unimaginably long, longer than the current age of the universe, by a factor of roughly 10 to the power of 100. That is, a 1 followed by 100 zeros. Compared to that, the 13.8 billion years since the Big Bang are like a brief sigh. In that sense, we are safe, at least for any span of time that has meaning to human minds or civilizations. The universe may be precarious on paper, but functionally, for us, it is steady. The James Webb Space Telescope gives us a way to test this picture indirectly. By observing the earliest galaxies, Webb is measuring how cosmic structure formed when the Higgs field was still settling after the Big Bang. If there had been even a small instability in the field, some early tendency to slide toward a different vacuum, we might see its fingerprints in how matter clumped together, in the spacing of galaxies, in the subtle statistics of cosmic structure. So far, the data show remarkable consistency. For more than 13 billion years, the Higgs field appears to have remained calm enough for galaxies to form and stars to burn, as our models roughly expect. That long, quiet persistence is reassuring. But calm does not always mean safe in an absolute sense. Even in a metastable state, small perturbations, tiny disturbances, could, in principle, trigger a transition. Theoretically, extremely high-energy events, such as collisions of ultra-energetic cosmic rays or the last whispers of evaporating black holes, might nudge the field in dangerous ways. This is why, from time to time, people have worried that human-made particle colliders, like the Large Hadron Collider, might produce energies high enough to disturb the Higgs field. Others have pointed out that the universe has already endured far more violent collisions from natural cosmic rays for billions of years without collapsing. The sky has been conducting its own high-energy experiments long before we learned to build accelerators. Astrophysicist Neil deGrasse Tyson once remarked that the universe is under no obligation to make sense to us. The Higgs field seems to embody that thought. It makes precise mathematical sense in our theories, and yet carries within it the possibility, however remote, of undoing everything it helped to create. At Fermilab and other laboratories, ongoing analyses of the top quark, the heaviest known fundamental particle, continue to refine our understanding of Higgs stability. The way the Higgs field interacts with the top quark is crucial in determining whether our vacuum is stable, unstable, or metastable. Every new decimal place in those measurements tells us a little more about which side of the cosmic balance we truly occupy. So far, the numbers suggest that we are perched very near a razor's edge, a universe delicately balanced between creation and collapse. The European Space Agency has poetically called this a universe poised on the knife edge of existence. It is a soft phrase for something terrifyingly precise, a shift of even a trillionth of a percent in the Higgs potential could, in principle, mark the difference between eternity and oblivion. Even the concept of temperature loses some of its familiar meaning when we talk about the Higgs field. Cool a system all the way down toward absolute zero Kelvin, the coldest possible temperature, and the Higgs field does not go silent. It still hums, filling space with its constant presence. It defines what empty means in the first place. Its gentle, persistent value is the background tone that allows matter to exist at all. Carl Sagan once wrote that somewhere, something incredible is waiting to be known. Perhaps one part of that something is this: the realization that everything we see, everything we love, rests on a quantum decision made billions of years ago, a decision that may not yet be final. We live, it seems, not in a truly stable universe, but in one that only pretends to be stable. It's calm, a long, fragile performance lasting across cosmic ages. We are balanced on that thin, invisible lake of energy, floating above a deeper truth we cannot yet touch. The surface is smooth, the stars reflect beautifully in it, but the depth below remains unknown. But if the Higgs field is indeed trapped, if this calm is only an illusion, what happens if it ever breaks free? What would really happen if the Higgs field changed its mind? If one tiny quantum event, somewhere in the dark, chose a different path? At the heart of everything, you know, the stars overhead, the atoms in your bones, the faint blue light that brushes your skin, lies one quiet presence, the Higgs field. It hums invisibly through all of space, a gentle background note that never switches off, giving weight and structure to the universe. Without it, particles would rush around at the speed of light, unable to slow down long enough to form anything at all. Because of it, matter can linger, gather, and become worlds. And yet, if that field were ever to shift even slightly from its current value, it could erase every one of those worlds, not symbolically, not as a story, as a real possibility that falls straight out of the equations of quantum physics. Sidney Coleman once called it the most terrifying consequence of quantum tunneling, a quiet line of math with enormous implications. Quantum mechanics, at its core, tells us that the universe is never entirely still. Even in what we call its calmest state, energy flickers and ripples beneath the surface. Empty space is not truly empty. It seethes with momentary flashes of activity. Pairs of particles appear and vanish, borrowing energy from nothing for a fleeting instant, only to repay it almost immediately. This restless dance lets particles do things that would be impossible by the calmer rules of everyday experience. They can tunnel through barriers of energy they do not have the strength to climb over. Electrons do this inside atoms when they jump between levels. Radioactive particles do it deep in the hearts of stars and within unstable nuclei. Tunneling is not an exception. It is woven into the way the universe functions. In principle, the Higgs field can do it too. It can tunnel through the invisible energy wall that separates our current state, a false or metastable vacuum, from a deeper, lower energy state of reality. It does not need a push. It only needs the right kind of quantum fluctuation at the right time and place. If that happened, it would begin very small, somewhere in the vastness, perhaps in a distant corner of the cosmos we will never see. A single quantum fluctuation might nudge the Higgs field into a slightly different configuration. A tiny region of space would suddenly remember that it could exist in a state with lower energy, a truer vacuum than the one we inhabit now. That microscopic region would collapse into the new state, forming a little bubble of true vacuum. Inside it, the Higgs field would settle at its new value. At first, the bubble might be smaller than an atom, but once it forms, the equations say nothing can stop it. The edge of the bubble would become a front where the old vacuum is replaced by the new, a moving boundary between two versions of reality. That boundary would expand at essentially the speed of light, consuming everything in its path: stars, galaxies, atoms, the quantum foam of space-time itself. Not with fire, not with thunder, not with shock waves we could hear, just a smooth, unstoppable wave of transformation sweeping across the universe. Physicist Joseph Licken at Fermilab once put it in a phrase that lingers: the universe could end not with a bang, but with a bubble expanding at the speed of light, changing everything we know. Inside that bubble, the rules would be rewritten. The constants of nature, the mass of the electron, the charge of the proton, the strength of the forces, even the speed of light could all take on different values. Chemistry as we know it would no longer work. Atoms might not be able to bind, or if they did, they would bind into something unrecognizably different. Every bond, every structure, every equation that currently defines existence would dissolve in the transition. NASA's Goddard Space Flight Center has described this kind of event as a quantum phase transition on a cosmic scale, the vacuum choosing a new identity. From the point of view of physics, it is not destruction in a moral or emotional sense. It is simply change. One configuration of the fields giving way to another. The way water can become ice or steam. But from our perspective, bound to this particular arrangement of constants, it would look like absolute oblivion. The eeriest part is how quiet it would be. We would never see it coming. If a vacuum bubble began forming in a galaxy billions of light years away, its edge would already be racing toward us at light speed. Light from that distant place would still show us normal stars, normal galaxies, a normal night sky. No telescope, no detector, no warning signal could outrun the bubble itself. By the time it reached us, we would be gone along with the telescope, the Earth, and the atoms that once made both observer and observation. In quantum physics, this kind of fate is called tunneling decay. It is a rare event that could, in principle, happen at any moment or perhaps never at all. The probability is low, staggeringly low, but not strictly zero. At CERN and other research centers, scientists have tried to estimate this risk by plugging in the measured mass of the Higgs boson and the top quark, the heaviest known fundamental particle. Their calculations suggest that we live in what is called a metastable vacuum, not the absolute ground state of energy, but a state that could eventually give way over an enormous timescale. As theorist Jan Elias Miro once put it, the Higgs boson seems to tell us that the universe sits on the edge of stability. It could last for billions upon billions of years, or in principle, it could decay tomorrow. The equations do not pin down a precise date. They only assign odds over vast spans of time. The James Webb Space Telescope, peering deeper into the past than any instrument before it, observes a universe that has remained remarkably uniform for over 13 billion years. That quiet consistency reassures us. The Higgs field has not fluctuated in any wild or dangerous way since the early universe. If it had, we would not be here. At the same time, this stability hints that if our vacuum is false, it is astonishingly robust. The field has stayed in its current state through the birth and death of stars, through the growth of galaxies, through all the chaos of cosmic evolution. The Planck mission, which mapped the cosmic microwave background, showed that the structure of the universe depends delicately on the exact value of the Higgs field. If that value had been even slightly different, if the field had been a bit stronger or weaker, galaxies might never have formed. The universe could have remained a thin, almost featureless haze. It is a balance so fine that even a tiny quantum tremor, in theory, could undo it. Coleman's equations go further. He calculated the rate at which a false vacuum, like ours might be, could decay by tunneling. The number that emerges is unimaginably small. A typical lifetime on the order of 10 to the power of -100 in inverse years, which corresponds to something like 10 to the power of 100 years as a characteristic timescale. That is, a 1 followed by 100 zeros. It is a span of time beyond human intuition, beyond the lifespan of stars, beyond even the slow fading of black holes. In practical terms, it means our universe could survive long after every star has burned out, long after galaxies have dispersed, long after even black holes have evaporated into faint whispers of radiation. And yet, despite that comfort, the possibility remains in the math, a quiet ghost, haunting the equations of physics. Stephen Hawking once reflected that a vacuum metastability event would be the ultimate cosmic disaster. A bubble of true vacuum could appear at any time, and we would never see it coming. There is a strange irony in this. The very quantum tunneling that might allow such a bubble to form is also the mechanism that enables nuclear fusion inside stars, the decay of heavy elements, and the ongoing life cycle of the cosmos itself. The universe's ability to change, to explore new configurations, is what makes it creative, and also what makes it, in a deep sense, dangerous. If the Higgs field ever truly changed its mind, the energy released in that transition would dwarf all known cosmic events. When two black holes merge, they can release energy equivalent to several suns, converted entirely into gravitational waves, a burst more powerful than all the stars in their host galaxies combined for a moment. But a vacuum decay would be something else entirely. It would not just release energy within the existing framework, it would transform the framework itself, turning all of space into a new, lower energy fabric. It would be as if the universe took a single silent breath and exhaled into a completely new reality. NASA astrophysicist Michelle Thaler once summarized the idea with a soft kind of honesty. If the Higgs field shifted, it would not be the end of everything. It would be the beginning of something else. We just would not be there to see it. That may be the most haunting part. The universe may be perfectly safe on all human timescales, or it may already be in the process of changing, its bubble expanding somewhere far beyond the horizon of what we can observe, and we would never know. Still, most physicists agree that if our vacuum is metastable, its lifetime is so long that it will likely persist for trillions upon trillions of years, far longer than any star can burn, any galaxy can hold its shape, any trace of life can endure. In the grand rhythm of the cosmos, we are granted time, more time than anything we know how to picture. Yet the thought lingers, a quiet echo beneath all that stability. What if one day, one fluctuation, one ripple in the Higgs field simply chooses differently? What if a single quantum event, the kind that happens countless times every second, is the one that finally tunnels through the wall, the one that changes everything forever? The silence after such a change would not be emptiness. It would be the hush of new physics taking shape, a new vacuum, a new symmetry, a new universe unfolding where ours once was. And somewhere within that thought lies the most chilling question of all. What if it is already happening, just far enough away that its wave has not reached us yet? Out there, beyond the reach of every telescope you and I will ever build, in a region of the cosmos from which no signal can ever return, something silent could already be on its way toward us. Not a fleet of stars or a storm of comets, but something far stranger. A wave without color, a horizon without light, a bubble of true vacuum, expanding at the speed of light and rewriting the laws of nature as it goes. According to the calculations of Sidney Coleman and Frank DeLucia, if the Higgs field were to suddenly tunnel into a lower energy state, the change would not unfold slowly like a melting glacier. It would begin in a region of space so small you could not meaningfully picture it, an infinite decimal patch, smaller than an atom, and then grow unstoppably, limited only by the speed of light itself. Inside that bubble, every field would rearrange itself around the new vacuum. Outside it, everything that once existed would cease, not by burning or breaking, but by being gently overwritten. There would be no flash to mark the boundary, no thunderclap, no shockwave, just the quietest erasure imaginable, a transformation so complete that no trace of the old universe would remain to remember it had ever been. Coleman once described it with a kind of haunting calm. The bubble, he wrote, would expand at nearly the speed of light, and there is no way to see it coming. When it arrives, it is already too late. The front of the wave and the end of our version of the universe are the same event. For decades, cosmologists have tested this unsettling picture against the numbers. If our universe truly sits in a metastable vacuum, then somewhere, at some unimaginable distance, such a bubble could already have formed. Because its edge would move at light speed, any signal announcing its birth would arrive no sooner than the bubble itself. There is no early warning. By the time the front of the wave reaches us, every photon that could have carried a message about it is gone. NASA's Goddard Space Flight Center once summarized it in stark terms. If a vacuum transition began somewhere in the observable universe, we would not observe its approach. The front of the wave and the end of the universe coincide. It is a strange kind of paradox, a cosmic doomsday that can never be seen, measured, or feared in time for that fear to make any difference at all. To get some intuition for how it would work, physicists build models of quantum fields and let them evolve in simulations. The Higgs potential, the energy landscape that defines the field's behavior, looks in these models like rolling hills and valleys, with several possible dips. Our universe appears to sit in one of those dips, but not necessarily the deepest one. If the field ever slips over the barrier into a lower valley, that descent would release energy across all of space at once, not as an explosion, but as a redefinition of what ground state means. The bubble wall, the edge between the old and new vacuum, would then expand outward, converting everything in its path into the new, lower energy form of reality. It would not be an explosion in the way we know explosions. There would be no blast of hot gas, no flame, no debris. Instead, it would simply redraw the rules inside the bubble. The masses of particles, the strengths of forces, the charges that define chemistry could all take new values. Researchers at the European Space Agency have compared it to a phase transition, like ice melting into water or water boiling into steam, except this time, the thing-changing phase is the structure of reality itself. And unlike a pot of water cooling back down, there is no going back once the universe has chosen the lower energy state. If such a transition had started at any point within our observable universe in the past, we would already be gone. The fact that we are still here narrows the possibilities to two. Either the vacuum decay has not begun anywhere within our cosmic bubble, or it began so far away that its wavefront simply has not reached us yet. The James Webb Space Telescope and the Planck satellite allow scientists to peer into the universe's earliest light, the cosmic microwave background and the faint glow of infant galaxies. So far, every observation points to remarkable stability. No large-scale phase transitions, no odd scars in the sky, no ripples that would betray a recent shift in the Higgs field. The vacuum appears to have held its present form since the universe cooled after the Big Bang, roughly 13.8 billion years ago. 13.8 billion, read as 13.8 billion years. And yet, Coleman's mathematics has not been overturned. If the Higgs boson's measured mass, around 125 giga-electron volts, and the top quark's mass, around 173 giga-electron volts, are both correct, then our universe seems to sit near the edge between fully stable and truly unstable. stable enough to last for times far longer than the current age of the cosmos, but not guaranteed to last forever. At Fermilab and at CERN, new experiments continue to refine these values, shaving off uncertainties, trying to understand exactly where the Higgs field lies on its energy landscape. Each new decimal is like adjusting the focus on a lens, bringing into sharper view whether our universe is genuinely safe in the deepest sense, or only suspended in a long, precarious pause. Physicist Brian Cox once reflected on this eerie balance, saying that we live in a universe delicately poised between existence and non-existence. The fact that it has not collapsed, he suggested, is both deeply reassuring and quietly unsettling. It means the laws we rely on have held without fail so far, and that they also contain within them the blueprint for their own replacement. If the bubble exists somewhere out there, what would it look like to anyone inside our current physics? The honest answer is, it would not look like anything at all. Its wall would outrun any information that could announce it. There would be no visual cue, no growing circle in the sky, no roar. From the perspective of an observer, there would be only continuity and then nothing. In less than a fraction of a microsecond, every atom, every star, every galaxy would be gone. Their fields and particles surrendered to the new vacuum's rules. The expansion would continue forever, or as long as there is old vacuum left to convert, eating its way through all of space until only the new phase of reality remains. Within that new framework, it is possible that new forms of matter could arise. New atoms, new forces, new ways for structures to form. New stars might burn with different light. New chemistry might weave new kinds of complexity. There could, in principle, be new life, built on unfamiliar rules, but none of it would be connected to what came before. No memories would survive the transition. No fossils of our old constants would remain. Scientists in NASA's Cosmic Origins programs have sometimes referred to this as a kind of cosmic rebirth through annihilation, a universe transforming itself beyond recognition. It is unsettling, but there is also an odd piece in the idea. This would not be a disaster happening to the universe from outside. It would be an evolution inside it, a continuation of the same quantum rules that allowed the Big Bang to give way to stars, and stars to give way to planets, and planets to give way to life. Perhaps that is why many physicists can speak about it calmly. In one sense, this scenario does not threaten us in the way a storm or an impact does. By the time it matters, there will be no us left to be threatened. In a larger sense, it completes the same story that began with the first burst of creation: energy, transforming, rearranging, starting over in a new key. Still, there is something hypnotic about imagining that even as we talk and breathe and look at familiar screens, somewhere beyond our cosmic horizon, a bubble might already be growing, expanding silently through the void, passing through galaxies whose light will never reach us, slipping past stars that will never know they were touched, gliding under the gaze of telescopes that cannot point that far. If that is true, if the wave is already on its way, then by the time its lightless edge reaches our part of space, there will be no one left to name it, no eyes to witness its strange beauty, no instruments to record its passing. Just a final symmetry, the universe returning to a simpler state, the complications we call structure and life dissolving back into a quieter pattern. Astrophysicist Claudia de Rham once expressed the idea gently. Perhaps what we call the end is just a phase transition, the universe moving on to a different, quieter state. So the next time you look up at the night sky, that still sea of stars that feels so permanent. It is worth remembering that it is stable, yes, but only for now. We live inside a balance so finely tuned that it can only be temporary on the longest scales, and maybe somewhere out in the unreachable distance, that balance has already begun to shift. Because if the universe can begin with one sudden burst of creation, it might also end with one silent bubble expanding through everything it ever made. But before we fade into that unseen horizon, there is one more mystery tugging gently at our thoughts. One last question, hovering at the edge of measurement and meaning. Can we actually detect how fragile reality truly is? How fragile is the universe, really? From far away, it looks eternal, galaxies drifting in a quiet ballet, stars burning with an almost mathematical rhythm, and the same laws of physics holding steady across billions of light years. It feels unshakable, like a story that will never end. But under that calm surface lies a question that keeps physicists awake at night. Is the very foundation of reality truly stable, or just pretending to be? Thanks to CERN's Large Hadron Collider, the most powerful machine human hands have ever built, we now know the universe better and stranger than we ever expected. In the year 2012, two giant detectors deep underground, called ATLAS and CMS, caught the faint traces of a new particle, the Higgs boson, the long-sought ripple of the field that gives mass to everything with weight. Its discovery completed what we call the standard model of particle physics, tying together decades of theory and experiment. For a moment, it seemed like closure, but then came the measurement that wiped away the comfort: its mass. The Higgs boson weighed in at around 125.1 giga-electron volts. On its own, that is just a number. Combined with another number, the mass of the top quark, around 173 giga-electron volts, it becomes something deeply unsettling. Those two values together suggest that the Higgs field is not sitting in perfect stability. It is balanced on a razor's edge between existence and collapse, in a state physicists call metastability. Imagine holding a glass sphere in your hand. From the outside, it appears flawless, smooth, clear, cold. But hidden within the glass runs a hairline fracture, invisible from the surface. The sphere seems solid. It might sit on a shelf for ages without incident. And yet, under the right stress at the right moment, it could shatter without warning. In that metaphor, the universe is the glass sphere. The hidden fracture is the metastable Higgs field. In 2013, theoretical physicist Gian Giudice, head of CERN's theory division at the time, described it this way: the measured mass of the Higgs boson tells us something profound, that the universe is perched on the edge of stability, not settled in the deepest possible vacuum, but resting in a false one. If that is true, then the Higgs field, the energy fabric filling all of space, could, in principle, collapse into a lower state. If it ever did, every particle, every law, every atom would either vanish or transform beyond recognition. Not because something broke in the usual sense, but because the very definition of something changed. Before panic has a chance to take hold, there is another crucial piece of the story. The timescale for such a decay, according to Coleman's equations, is beyond ordinary comprehension. If the universe is metastable, the probability of a transition in any given year is so tiny that the expected time before it happens could be around 10 to the power of 100 years, that is, a 1 with 100 zeros after it. longer than the combined lifespans of all stars that will ever shine, longer than any meaningful concept of time as we usually imagine it. Still, the fact that it could happen at all, that the laws of physics themselves might be temporary, leaves many scientists quietly awed. At CERN, some of them half-jokingly call this the beautiful danger of the Higgs, a field that makes existence possible, and at the same time hints that existence might be contingent. To understand just how delicate this situation is, researchers study the relationship between the Higgs boson and the top quark, the heaviest elementary particle we know. The top quark interacts very strongly with the Higgs field. Its precise mass influences how sharply the Higgs potential curves, how the energy landscape of the field is shaped. A slightly heavier top quark would tilt that landscape toward instability. A slightly lighter one would nudge it toward safety. As Fermilab physicist Don Lincoln likes to explain, it is as if the universe is balanced perfectly between two cliffs, firmly on neither plateau, yet somehow still standing. Measurements at the Large Hadron Collider keep refining this balance. With each new run, protons are accelerated to about 99.9999% of the speed of light and smashed together. The debris of those collisions, tiny sprays of particles recorded in their detectors, tells us about the shape of the Higgs potential. With every update, the picture grows sharper and more delicate. NASA scientists sometimes describe this balance as a kind of cosmic fine-tuning that surpasses anything we can engineer. The difference between stable forever and eventually decays is written in decimals, hidden in the fifth or sixth significant figure of a particle's mass. A tiny change in those digits would mean a completely different fate for reality. The Planck satellite, launched by the European Space Agency, mapped the cosmic microwave background, the afterglow of the Big Bang, with exquisite precision. Its data show that our universe has remained astonishingly uniform for about 13.8 billion years. 13.8 billion, read as 13.8 billion years. There are no scars in that ancient light that our universe look like vacuum decay. No evidence that the Higgs field has suddenly fallen through to a deeper state. If a bubble of true vacuum has ever formed, it did not do so within the part of the cosmos we can see. And yet, when physicists simulate the very first instance after the Big Bang, in the first trillionth of a second, the math suggests that things should have gone very differently. Temperatures then reached around 10 to the power of 30 Kelvin, that is, a 1 followed by 30 zeros on the Kelvin scale. At such unimaginable heat, any false vacuum should have been destabilized. The Higgs field, according to naive calculations, ought to have rolled straight down into a different state. The universe as we know it should never have had a chance to cool into stars, atoms, or us. But it did. Something perhaps cosmic inflation, that brief burst of accelerated expansion, perhaps subtle quantum effects we do not yet fully grasp, seems to have stabilized the Higgs field just long enough for the universe to slip through this dangerous phase and settle. That survival has become one of modern cosmology's quiet obsessions. How did we make it through the very moment when the equations say we should have vanished? ESA cosmologist John Ellis once joked that maybe the universe just got lucky. Or maybe we still do not understand how lucky we really are. The James Webb Space Telescope is now helping to test these ideas more directly. By peering into the faint light of the first galaxies, Webb reveals how matter began to cluster under the influence of mass, a property rooted in the Higgs field. If the field had fluctuated differently over cosmic time, galaxies would have formed at different epochs, or taken different shapes, or perhaps never formed at all. So far, Webb's data suggest a cosmos that is astonishingly consistent. Structures appear roughly when and where our best models say they should. Stable enough to allow complexity to arise, unstable enough to keep evolving. It is as if the universe is neither frozen nor chaotic, but held in a delicate balance, always on the verge of becoming something more. Physicists often compare this state to a candle flame in a still room. The flame burns steadily, feeding itself, maintaining its shape, but it is not invincible. A slight change in the air, a small draft, a different mixture of gases, and it would flicker and vanish. The flame, like the universe, is self-sustaining, but not unbreakable. To probe this fragility more directly, theorists use what they call the vacuum stability line, a boundary drawn in a mathematical plane whose axes are the Higgs mass and the top quark mass. When you plot these values, the plane divides into three regions: stable, unstable, and metastable. Our measured values place our universe squarely in the middle band, not plunging toward instant doom, not safely anchored forever, just in between. The position is so oddly specific that some scientists have begun to nickname it a kind of Goldilocks zone of existence. Not too stable, not too unstable, just finely tuned enough to linger. But how do you measure the fragility of something as vast and intangible as the cosmos? The answer is surprisingly humble. You measure it by watching its smallest parts. Every proton collision at CERN, every radioactive decay measured in a quiet laboratory, every whisper of cosmic radiation captured by a distant satellite carries information about the fields that hold reality together. By understanding the Higgs field, we are, in a sense, taking the universe's pulse, its rate, its rhythm, its quiet vulnerabilities. The European Space Agency's Euclid mission, launched in the year 2023, will extend that checkup by mapping dark matter and dark energy across billions of galaxies. By watching how space expands and how structures grow over cosmic time, Euclid can indirectly test whether the strength of the Higgs field and related parameters has shifted, even slightly, over billions of years. If any tiny drift were detected, it could hint that the vacuum itself is evolving, slowly, imperceptibly to us, but inevitably on larger scales. Physicist Sabine Hossenfelder has remarked that we may already be measuring the instability of our universe without fully realizing it in the small mismatches between what our theories predict and what our experiments actually see. Those mismatches, tiny as they are, might be the echoes of a deeper truth, the faint creaking of that cosmic glass sphere as it bears its own weight. The fragility of the universe is not something we can feel with our skin or see with our eyes. It is written in decimals and probabilities, in error bars and confidence levels, in the invisible hum of the Higgs field that wraps around every atom you have ever touched. Even now, that field is moving through you, through the room you are in, through the earth beneath you, the same field that moves through stars and galaxies and the thin vacuum between them. So yes, in a way, we can measure it. We measure it in the quiet stream of data pouring out of colliders and telescopes, in the steady consistency of starlight that has crossed billions of years to reach us, in the simple fact that, despite all the ways the universe could have failed to hold together, it has not done so yet. The universe may be metastable, a glass sphere poised above eternity, but it endures beautifully, improbably, for now. And as long as it does, we keep asking questions. not out of fear, but out of curiosity and precision. Because to understand fragility is also to understand why anything can exist at all, why order can rise out of chaos and hold. Yet, even as we measure and observe and refine our models, one thought lingers like a soft echo. If the universe truly hangs between stability and collapse, then perhaps its calm is not entirely natural. Perhaps, somewhere, somehow, something is quietly keeping it in balance. If everything we know could vanish in an instant, what are we really living on? Sidney Coleman once shared a line that still drifts through the quiet corners of physics. "I know how to destroy the entire universe." He was not being dramatic. He was not speaking in metaphor. He was talking about an equation, a calculation that revealed something deeply unsettling, that the ground beneath all existence might not be as firm as it feels. Every particle, every breath of air, every beam of light exists because of one invisible structure, the Higgs field. It is everywhere, woven through every cubic centimeter of the universe, quietly giving mass to matter. Without it, electrons would not settle into orbits, stars would not burn, atoms would never hold together long enough to become dust, planets, oceans, hands. What Coleman realized was painfully simple and terribly real. This field, the foundation of everything, might be unstable. According to quantum field theory, the Higgs field may not be resting in its true lowest energy state. Instead, it could be trapped in a false vacuum, a shallow valley of apparent stability surrounded by deeper wells of energy. The universe, in that picture, is like a ball resting in a small dip on a hillside, not at the bottom of the mountain. A tiny fluctuation anywhere in space could, in principle, allow the ball to tunnel through the hill and drop into a deeper valley. NASA's Cosmic Origins team sometimes described this scenario as a catastrophic restructuring of reality itself. If such a transition were to occur, the Higgs field would reconfigure everywhere, all at once, changing the laws of physics in an instant. Matter, as we know it, would lose its form. Light might no longer travel the way it does now. Space and time, the very framework in which events unfold, could dissolve into something unrecognizable. There would be no explosion to mark the moment, no siren, no flicker in the sky, no pain. Just a wave spreading at the speed of light, converting everything into a new kind of vacuum, silent and complete. When scientists at CERN discovered the Higgs boson in 2012, they rightfully celebrated a triumph of human understanding. The last missing piece of the Standard Model had finally appeared in the data, but hidden inside that triumph was a whisper of danger. The Higgs mass, measured at about 125.1 giga-electron volts, placed our universe on the razor's edge between stability and collapse. As CERN theorist Gian Giudice put it, we live in a universe poised between two fates, one stable, one doomed, and yet somehow balanced between them. In other words, according to the Standard Model, our universe is metastable, not collapsing, not guaranteed safe, just temporary. The numbers line up in an eerie harmony. If the Higgs field's energy had been only slightly higher, the universe would have expanded too quickly for galaxies ever to form. Matter would have thinned out into diffuse nothingness. If it had been slightly lower, everything might have collapsed back in on itself within microseconds of the Big Bang. Instead, we exist in the narrow window between those extremes, a slim, shimmering interval where structure is possible, where stars and chemistry and life can arise. The James Webb Space Telescope has now captured light from faint galaxies glowing in the universe's first few 100 million years. Those galaxies should not exist if the Higgs field were wildly unstable. Yet there they are, delicate clusters of newborn stars, shining across more than 13 billion years to reach us. Every photon web detects from that young era, every distant spark in its images, is quiet proof that the field has held steady long enough for those structures to form and persist. ESA physicist John Ellis once remarked that, according to our equations, the Higgs field could have collapsed long ago, but it did not. Here we are, billions of years later, still existing, still measuring, still asking why. The fact that it hasn't collapsed is a mystery that continues to haunt cosmology. One idea suggests that the violent inflationary period in the early universe, the rapid, almost unimaginable expansion just after the Big Bang, may have flattened the Higgs field's potential, smoothing it out just enough to prevent it from tunneling into a deeper state. Another idea is that unknown physics, perhaps tied to dark energy, or to quantum gravity, or to fields we have not yet discovered, helps keep it pinned where it is, like a hand gently resting on the ball to keep it from rolling. Whatever the cause, the result feels almost miraculous, an unstable reality that has persisted for nearly 13.8 billion years. Data from the Planck satellite support this delicate picture. The cosmic microwave background, the universe's oldest light, shows no scars consistent with vacuum decay, no strange distortions that would suggest the Higgs field flipped to a different value. Instead, it looks smooth, calm, almost sleepy, as if the field has been resting in the same configuration for eons, dreaming our existence into being. But dreams can end, and so the question remains, what if it wakes? That question is not just poetic, it is, in principle, measurable. If an ultra-high energy cosmic ray, or some collision beyond the reach of our current accelerators, were to trigger a local phase transition, the false vacuum could collapse in that tiny region. A bubble of true vacuum would form and begin to expand, erasing the old vacuum as it went. Physicist Joseph Liken once said in an interview that, if this picture is right, then one day, perhaps billions of years from now, a bubble will appear somewhere and wipe us out. Then he smiled and added the strange comfort. The good news is that it would happen at the speed of light, so you would never see it coming. That is the paradox we are left with. We live on borrowed stability, on a field that might not be truly at rest. Yet it is exactly this fragility that makes the universe as rich as it is. If the Higgs field were too stable, frozen in an unchanging configuration, nothing would ever happen. No stars would burn, no galaxies would evolve, no heavy elements would form in stellar hearts. Life would have no foothold. Carl Sagan once wrote that we are a way for the cosmos to know itself, and perhaps, in that knowing, there is a quiet miracle. The fact that awareness can bloom in a universe so delicately balanced between being and not being. A consciousness that can look back and notice how precarious its own stage is. When the James Webb Space Telescope peers deeper into the past, it is also peering into the universe's patience, tracing how long this metastable balance has lasted. Every faint, redshifted galaxy Webb records is one more moment in which the Higgs field chose again not to change. Billions of years of cosmic stillness, at least in this one crucial parameter, and yet, no law of physics promises it will stay that way forever. The universe is under no obligation to preserve us. In a quiet note about cosmic stability, one NASA release put it simply, it continues, for now. And for now, they suggested, is enough. So if everything could vanish in an instant, what are we living on? We are living on the edge of probability. on a field that hums in silence, holding everything in place for one more heartbeat, one more breath, one more rotation of the Earth. The Higgs field, unseen and untouchable, has been steady longer than any star, any atom, any thought. And as far as we can tell, it is still steady tonight. That is the wonder tucked behind Sidney Coleman's warning. He was not really predicting doom. He was describing perfection, a universe balanced so precisely that even the smallest vibration could erase it, and yet it endures. For now, the equations hold. The vacuum remains false, and beautifully so. The stars keep shining. The fields keep humming. Reality keeps choosing, moment after moment, to go on. So tonight, as you listen, as the hum of the universe settles softly around you, let that thought become something gentle instead of frightening. You are floating on the calmest ocean that physics has ever described, an invisible sea of fields and probabilities, and it is still holding you. If this quiet voyage through the universe has brought you even a small moment of peace, I am grateful you chose to be here in this shared stillness. Your presence, your listening, is like a tiny point of light in all this vastness, a reminder that the universe has grown not just stars, but minds that can wonder about them. Now, let the questions loosen their grip. Let the idea drift away that even in a universe balanced on almost nothing, it is still choosing, for now, to exist and to hold you. Rest your thoughts like dust settling in a sunbeam. Feel the night fold gently around you. Sleep peacefully under its fragile light. Good night, dreamer of stars.